Welcome back to Fierce AI Week's engineering track. And next up, we have Mark Lippitt, CEO and President at XMOS, with a session entitled Embedding a Secure Solution for the AIoT Big Bang. XMOS is a gold sponsor on our event. And if you haven't already, please take some time to explore our resource center, where you can find out more information on XMOS as well as our other sponsors. Sending it over to you now, Mark.
Hey, thanks, Matt, and thanks everybody for your time. As Matt just said, we'll be talking about embedding a secure solution for the AIoT Big Bang. So we'll spend a few minutes talking about that, and particularly some of the areas that we're seeing where the artificial intelligence is starting to collide with the Internet of Things in the short and medium term. Many of these devices will already be quite familiar to you. I'm sure we're all familiar with smartphones, and nowadays also with smart speakers. And we've probably all seen smart fridges, at least on TV and at CES, although they're not quite as pervasive in modern smart homes. Certainly, TVs, smartphones, speakers are all starting to increase the level of intelligence that's present at the very edge of the network, at homes, in our commercial environments, cars, and so on and so forth. A couple of areas that you may not be quite so familiar with, which we're seeing at the sort of leading edge of the design cycle, is intelligence being embedded in things like exercise bikes for social exercise, and also intelligent devices starting to monitor our health and well-being when we're in the home. And I think we'll increasingly start to see those trends becoming more and more pervasive in the short to medium term. So let's just move on and talk about one of the biggest use cases of artificial intelligence at the edge in today's society, and that's the use of voice. And I think voice is going to remain a cornerstone of AIoT for some time to come. And we've already seen the likes of Alexa and Google Home demonstrate the utility of voice. It's very convenient, and that shouldn't really be a surprise to us. It is the manner in which we choose to communicate with each other. But naturally, with a voice interface that's embedded in a machine, and particularly a machine that is connected to the cloud, that voice interface, the convenience of that voice interface, is delivered alongside some security and privacy concerns. Consumers are not particularly comfortable with the idea of all of the acoustic events in their homes being transferred to the cloud, but naturally they are interested in the utility of using voice in many use cases, some of which we can talk about in a minute. So the idea that you might be able to deploy a voice interface that not just isolates your voice, but also interprets your intent and acts independently of the cloud is quite intriguing. Now, naturally, there are other things that we need to be very cognizant of. We need to make sure that those devices interact well with each other. And critically, we also need to make sure that we can deliver these kinds of features, these kinds of functions, without breaking the bank, essentially, without creating devices that are too expensive for the broadest corners of society to actually gain the benefits of this technology. There's really no point. It's a real missed opportunity if, when we're delivering this high technology and the security and the privacy alongside artificial intelligence at the edge, that we can only deliver that to niches. We want to be able to make sure that we can appeal to the mass market, and that puts an additional limitation or an additional constraint on the technologies we develop, based on the cost of use, the cost of deployment. So before we come back to that, let's look at a couple of use cases. Smart cities. Now, this was purely driven initially, at least, by convenience. XMOS actually have designs in smart cities, in fact, in metro stations for dispensing tickets and dispensing advice on travel. Connectivity is not always present in these areas, so you can maintain that kind of service in contexts where cloud connectivity is not even possible, and deliver real utility. that's been actually this convenience aspect has been augmented significantly in previous months by the fact that we don't really want user interfaces in cities, in shared spaces, to require contact anymore. We'd much rather have voice-based interfaces to fulfill our needs in this context without actually requiring to use keyboards or other shared surfaces that might represent a threat to our health and well-being. So these kinds of smart city applications are actually growing in importance, not just for convenience, but also from a health aspect. Similarly, smart buildings. Initially, the utility of voice-enabling smart buildings, of adding intelligence into smart buildings, was perhaps to maintain security at access points, or perhaps to maintain the utility of meeting rooms, to ensure that if they're booked, there's people within them. But now we've gone beyond that to a situation where intelligent edge devices can not only determine your identity at the door, perhaps by using voice biometrics that might be augmented by face detection, but also delivering some sort of healthcare monitoring to make sure that people that are entering a building appear to be well. So another key, a new key dimension in today's world for intelligence at the edge. And of course, there's also things like social distancing criteria within shared spaces, within meeting rooms, within elevators, for example, that can easily be accommodated by intelligent devices that monitor human presence, human location, as well as offering the utility of voice-based interfaces. Perhaps on a slightly more sort of trivial side of things, there's those high traffic areas like coffee machines where clearly in today's world, at least, there's a requirement to touch the device. There is typically convergence of individual presence. All of these things can be facilitated in a more secure and in a healthier way by the deployment of smart intelligence at the edge to facilitate our movements and to facilitate our actions in response to either voice commands or simply our presence and an interpretation of our intent. Going slightly closer to home now, the home is an area where perhaps concern about health, insofar as transmission is concerned of viruses and so on, it's perhaps not quite such a big concern, and perhaps this is more about the sort of utility and convenience. In a kitchen scenario, it's a classic example of where voice interfaces really work. Voice interfaces are of particular relevance when your eyes are diverted, your attention is diverted, when your hands are busy, possibly your hands are dirty. I'm sure we're all familiar with the sort of classic use case where somebody's kneading flour and their hands are very dirty, they don't want to touch their devices. So these are mostly convenience use cases where we actually want to control our equipment without having to touch it for those reasons. And this example of a hob overflowing is a great example. We might actually, for safety reasons, not want to go too close to that hob. A voice interface makes a lot of sense in that smart home context. Even things like washing machines. If you're walking to a washing machine with a basket of washing in your hands, you might say, "Hey, washing machine, please open the door." I mean, that sounds trivial, but actually there's a real use case here. A genuine customer in China who actually wanted to be able to tell whether the person that was talking to the device, and this was a general case in the kitchen, was a child or an adult. And they perceived safety issues with children interacting with some of these devices, and with a washing machine, they were particularly concerned about people playing hide and seek within the drum of the washing machine and the safety implications of that. So they actually wanted to make sure that even that environment was secured by a more intelligent deployment of technology at the edge of the network. And finally, something that we're all familiar with, I'm sure, is where we'd like some silence. Sadly, this doesn't work quite so well on your children, but a well-behaved smart home might collaborate with you when a phone call arrives and allow you to switch off the spin cycle on the washing machine, to turn down the smart speaker, and enable you to have a restful and relaxing conversation. So many of these use cases are sort of medium to longer term, but certainly we're finding in the short term that many of them are directly amenable to our existing lives and can be deployed readily to consumer electronics devices that already exist in our homes. So let's just watch a short video that gives us a brief glimpse of what that might be like. Now that video is available in full on the Fierce AI website, and the eagle-eyed amongst you will have noticed one of the most useful status indications of a smart home device, which is the indication of human presence. Knowing that a human is present allows power-saving features that otherwise cause a tremendous amount of power consumption that's completely wasted. For example, a smart TV that is waiting in standby with an active voice interface and an active voice processing pipeline when there are no people in the house. Those kinds of use cases can be readily avoided, saving significant power for the smart home of the future. So it may have looked just like a voice interface, but actually there was an interface of a multimodal sensing there, determining whether people were present and managing standby power states accordingly. So in order to really deliver on some of this promise, there are some interesting facets that need to be delivered. Now, clearly, the AIoT is not a meaningful market, and not a meaningful and targetable market. It's simply too broad. It represents an enormous fragmentation of markets, an enormous fragmentation of ideas of how we can deliver utility and convenience into our everyday lives. But there are certain themes that all of these things share in common. Voice interfaces, managing radar imaging and other cameras and so on are a heavy lifting compute problem. They're a heavy lifting and a diverse compute problem. These devices also need to deliver on efficient energy usage, as I mentioned, not just at the device level, but intelligent understanding of system level energy saving capabilities. And above all, they need to deliver on a low bill of materials. So being able to deal with fragmentation, being able to deliver on the performance requirements, doing so with energy efficiency and at a low cost is a pretty challenging set of problems to solve. Now at XMOS, some years ago, over 10 years ago, we conceived of a processor design that was uniquely capable of addressing the fragmentation in the Internet of Things. So this is before Edge AI was really an area of focus. And we developed a processor called the X-Core, which was uniquely flexible, capable of delivering flexibility at a hardware behavior level, at a processing and a control processing level, and thereafter also being able to deliver significant flexibility around digital signal processing. We're now in the third generation where we've added artificial intelligence into the mix as well. So we've now got 4 dimensions of compute: the ability to manipulate I/O like no other processor, control processing, DSP, and now also significant AI capability. And all of this is academically interesting until you acknowledge the fact that it's in a $1 device, which makes it commercially a very disruptive processor. Significant amount of integration of any one of those compute classes or all of them in a $1 device enables this kind of capability to proliferate not just beyond beyond current device classes, but also into consumer electronics and commercial electronics equipment that can be found in everyone's home. So when we look at our performance, we're the only processor that can deliver the level of flexibility that I described between those 4 classes of compute. But when we look at our performance and compare ourselves to our competitors, we tend to look along single dimensions, and we look at crossover processors as the most close competitor, as the class of processor that effectively competes for the same dollars in the bill of materials. Now, crossover processors are a relatively new category, and they describe themselves as delivering the ease of use of a microcontroller alongside the performance of an applications processor. Now, we've pushed more dimensions there. Alongside those two things, we deliver the I/O flexibility benefits that you might find in a field programmable gate array, and also some neural network processing capabilities that you might simply not find in other classes of devices designed for the edge. And each one of those vectors exists in a complementary manner. But when taken in one at a time, you can see that we're delivering all of that flexibility alongside order of magnitude improvements in performance for a device that costs less than the competition. So when I say disruptive, I'm talking about disruption in terms of our ability to deliver a platform that gets you to market that's uniquely flexible and also uniquely economical. Now, we're a processor company. We develop processors, but as you will no doubt be aware, that's only part of the solution. So we develop semiconductor devices. We also develop tools, and we develop libraries. And some of those libraries allow you to gain access to Xcore's unique capabilities, and some of those libraries are off-the-shelf libraries, if you like, for example, FreeRTOS, that device libraries that people are familiar with using. And you can use those libraries and those capabilities in combination under the guidance of an XMOS reference design to piece together your own unique application and deliver something really special to the market. We also have another route to market where we provide unique solutions. We provide our own solutions, demonstrating the capabilities of our algorithms and technologies in an application-specific product. And either one of those routes is equally valid for an XMOS customer. But what we really love to see is our customers taking our technology, taking the fundamental capabilities of our technology and doing something really special with it. And we really love to see that because it's exciting for us as a business, but it also allows us to watch our customers really thrive in a market where they can genuinely start to differentiate themselves, as opposed to perhaps reproducing Me Too products from an off-the-shelf solution. So how do we do it? So this is a sort of a dive into the hardware architecture. The first thing to acknowledge is we took a different approach from the very outset when we designed the Xcore device, the Xcore processor. Many SoCs, they have a small number of processor cores, and the operating system or some other executive crams all of the pieces of the application through that single pipeline and attempts to slice time in a fair manner between all those parts of the application. Now, because that processing resource is a shared resource, it makes guaranteeing timing performance and guaranteeing behavior of hard real-time code, or even generally code that's being reused, it makes guaranteeing that composability very difficult indeed. So we took a different approach. We actually, rather than having a single device, single processor core that is shared, we have lots of individual processor cores, which are each capable of doing exactly the same thing as their neighbors. And we connect those processor cores together using a switch infrastructure, and that allows us to construct an application that comprises I/O processing, control processing, DSP, and AI processing in a manner that where the individual parts of that design, where hard real time is necessary, the individual parts of that design don't interact in a disruptive or unexpected manner. So by spatially multiplexing the application like this, by spreading it out over numerous logical cores, we can make guarantees about performance that other processors simply cannot make. And that helps us when we're doing hardware emulation using a software programming model, for example, or when we're doing hard real-time DSP processing, or increasingly nowadays when we're doing AI processing that has hard real-time deadlines. We can look at our underlying hardware platform and make reasoned judgments about exactly how that platform is going to perform. So that's why we have a parallel architecture. Each tile, so there's two tiles in front of you, separated by a switch in the middle, has access to a very high-speed, tightly coupled memory, and the option to extend beyond that memory for larger models, perhaps, through an LPDDR interface. We also provide infrastructure to manage hardware protocol emulation. So, for example, hardware I/O protocols, and also in a limited number of cases, we have specific interfaces implemented, including high-speed USB and MIPI D-PHY. So those are the sort of principal elements, alongside a set of security tools, including one-time programmable memory, generators of random numbers, and so on. Those sort of foundational components required to build an intrinsically secure device. So this is X-Core AI, and as I mentioned, in terms of performance, outstanding performance, low EBOM, and high levels of energy efficiency. Now, in terms of what it looks like to deploy software on this device, is a representation on the left-hand side of a software stack, if you will, FreeRTOS across the middle. So above that layer is a very familiar application programming environment, and below that layer are things like accelerators, device drivers, and so on and so forth. Now, the key thing to recall here is that all of this is developed using embedded software. So things like PDM interfaces, I2C, I2S, LED drivers, and many more complex protocols can be delivered and employed using a simple software library on an otherwise general purpose platform. So here we've got two PDM interfaces to interface to two microphones. We have a keyword detector, which is probably a neural network, a DSP pipeline doing far-field microphone processing. We have our basic hardware interfaces for the audio path and other aspects of the human-machine interface. We have a neural network model, which for the sake of argument, let's say in this case would be a local dictionary. And then we have FreeRTOS with all of the application tasks running over, in this case, three logical cores, seamlessly sharing three logical cores. So what we've done there is using a purely software-based approach, we've created a bespoke, a customized microcontroller. And this kind of approach can deliver a solution that's differentiated, that embodies your special sauce, that can come to market in a matter of months rather than the years it would take you to develop a chip to do this product, using a sort of traditional software, it's a traditional semiconductor model. I'm sure you're curious about tools and development methodologies. One of our mantras, if you like, is ease of use, and the way that we deliver that is by using as many open source popular tools as we can possibly use, whilst also delivering the benefits and the intrinsic value of the underlying architecture. So if you're in the control domain doing control processing, you can use FreeRTOS as an abstraction and deploy that through an LLVM compiler suite, which takes in C, is a C-based compiler, and allows you to use all of the intrinsics of the X-Core architecture through C libraries. For the AI methodology, we use TensorFlow, TensorFlow Lite. We have tools that automatically translate models, and we also have a route through Onyx for various other abstractions like PyTorch and Caffe, for example. If you want to program on the metal, if you want to program, for example, a data flow architecture like you might use for DSP, then we also provide a lower level access to the underlying capabilities of the architecture, so you can piece together those flows. And of course, when you're building these kinds of products, typically, if for a fully highly integrated design that delivers real economy, you're going to want to do all the same at all of those things at the same time. So we have a single tool flow that exploits the fact that we have an underlying homogeneous architecture to deliver these disparate processing demands through the same tools, using a traditional embedded software approaches, and consequently delivering differentiated designs at very low time to market. So that's the main body of the presentation. So maybe I can just summarize. I think so far as the artificial intelligence of things is concerned, we're seeing real deployments, and some of them are approaching mass market. And we're also seeing not just convenience as a driver, but also we're seeing that things like COVID and so on are driving us further and further towards voice interfaces, touch-free interfaces, and touch-free human-machine interfaces that deliver real utility without us actually having to place ourselves in situations where we're not secure. Now that either may be because our data is being looked after at the endpoint, or it may be because the interaction with that machine has been tailored to maintain our security. Now, secure solutions, by definition, should be more independent of cloud services. That delivers the ability to or reduces the number of attack surfaces for hackers, and maintains the convenience of using voice interfaces for any number of consumer and commercial applications. We think that Xcore AI is a unique solution that delivers on the flexibility required to address the artificial intelligence of things, the fragmentation that we're going to experience as this kind of technology proliferates. It's sufficiently low cost to not just to deliver on existing commercial categories, but push intelligence into some of those electronics components where we've previously not seen that level of performance and that level of convenience and utility. And we've delivered a solution that not just cuts the umbilical cord with the cloud, if you like, but also intrinsically provides a secure platform on which to build really special and differentiated designs. And we are absolutely thrilled to bring Xcore AI to the market this year, and really looking forward to seeing what our customers can do with its unique capabilities. I think that's me done, apart from to say thank you very much for your attention.
Thanks everybody for attending today's Fierce AI Week engineering track that was presented by Fierce Electronics. Please join us back here tomorrow at 10 a.m. for our morning common keynote, Plug and Play AI, embedding cutting edge AI into business processes and applications. And then there's a keynote interview in the engineering track at 11 a.m. as indicated on the slide. On behalf of Fierce Electronics, I'd like to thank all our speakers for participating, as well as today's sponsors. That's XMOS, SensaMill, NXP, and MetaWave. Thanks again, and take care until then.